Let's start. Let's discuss what we had last time. So this is one of the example we introduced for a topology on R2. Actually, you can show that these two set of bases, they form a basis. Okay. So if you want to prove they form a basis, right? What's the definition of a basis for topology? Two criteria. The two criteria. Okay, so if you are a basis for topology in a metric space, you need to be able to find a basis element that contain point in metric space for everyone. Okay, and then something about intersection. Yeah. Yeah. So still, if you look at the intersection of two basis elements, okay, for every point inside there, there should be another basis element that contains those points where the whole basis is lying inside the intersection. Okay, and right, and then we want to show that actually they are the same. Okay, so one is finer than the other. Okay, in other words, you can show that the topology generated by B and the topology generated by B prime, one is finer than the other, then they are equal. Okay, so we have proof. Okay, we've proven the property to show that one topology is finer than the other. We can just use basis. Okay, we can just use basis to check. So what's that criteria? So let me go back. Okay. Go back a bit. Okay, so to show that one topology is finer than the other, if you know about their basis element, what can you do? You can check that for every point in your metric space, and if there's a basis element that contain X, okay, you should find another basis element from the other topology, okay, that contain that point as well, and at the same time it lies inside the first basis element. Okay, does it make sense or not? Does it make sense? What does it mean by T prime to be finer than T? Every open set in T is an open set in T prime. So if you found a basis element that contained in B, meaning that B is open in B prime. And in terms of basis element. So really I summarize these definition into these three pictures here. Okay, for every point, you can find a basis element that covers these points. And within the intersection, you can find another basis element. So note that you see in the second rectangle intersection, I didn't draw a rectangle anymore. You know why? I didn't draw a smaller rectangle. You know why? 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 Sorry? because the intersection is already a basis element. Okay, you can just take that as your basis element. For the third one, you can show that one open set is contained in the other. Okay. So this is the picture that you should see when you read the definitions. Okay. Those the definition you might think that there's a lot of word inside there, but those words is to describe some situation, okay, some condition, okay, that we imagine. So you need to be able to turn these words into some imagination that makes sense. Okay, not just a random bunch of paragraph. Okay, so this is one of the example we've seen in the last lecture. And another thing I want to remind you is the difference between topologies generated by bases and subbases. Okay. Still remember what's the topology generated by a basis? So you declare some set to be basis, okay, and satisfy the two property we mentioned just now. And then what are the open set there? What are the open set there in terms of these basis elements? A set U is open in the topology generated by basis if for every X in the U, you can cover it using a basis element such that that basis element lie inside U. Okay, it's very how to say, very similar. Okay, you want to find some open thing, open set, open ball, okay, that contain X, which that open set itself is contained in the bigger set. Okay, right. How about subbases? How about subbases? Huh? What's the difference between subbases and bases? Why sub? Sub is what? Smaller. How is it smaller? You look, the topology generated by subbases is you take the union of finite intersection. Okay, so that intersection is declared as a basis or open, right? Okay, like for example, previously, so this solves a very nice problem here, right? So if we have these two open ball, right? If we fix our B to be just open ball, this intersection here doesn't look like an open ball, right? But if we include subbases, then this kind of intersection we will declare it to be open. Does it make sense? Does it make sense or not? Does it make sense? So if I just take basis with open ball, okay, the intersection there might not be an open ball. So you need to have a smaller open ball that lies inside this intersection. But subbases solve this problem because I just declare this intersection to be open also. Okay. Does it make sense? Okay. Even though it doesn't look like open ball anymore, but it is an intersection of two open balls. Does it make sense? Okay, so this is the difference between the two. Any question or not? Any question? Okay. So if you don't follow what I said, better you bring out your definition. It's a good exercise if you cannot memorize the definition for now, just make a list. Okay, whenever I touch on that word, and then you immediately check the definition. Okay, because these things are not familiar to you, right? So you need to keep yourself familiarized with these terms. Okay. Any question from assignment, lecture notes, or other things, other stuff? Any question? So assignment 4 should be due this Friday, right? Do you guys need extension or not? Need? Yes, just GGME that. Most of you need. Okay, how long you guys want to extend? Also Monday, take a weekend. Okay, okay, sure. And I also released assignment 5 already, so that's the last one before exit. So we fix from Monday for assignment 4. The fine. Okay. Monday for assignment 4. Okay. Sure. So if you need some extra extension or some problem you met, you just come see me personally or email me. Okay. So let's start today's content. All right. Yeah, by the way, for the latecomers, right, we have extended our assignment 4 to next Monday. Better? Okay, good. All right. So we will introduce one definition for today. Okay, because we keep talking about an open set containing point X, open set containing a point X. Right? So we try to reduce our word. So we'll just define that U, so the set U in the subset of U in the topological space, not just metric space, is an open neighborhood of S, where this S is in X, if U is an open set containing X. Okay, so this is a little bit different from what you see in Moncrief, right? Moncrief, they just take it as neighborhood. Okay, they didn't mention open. So we will add in this open neighborhood here because we want to follow the convention that we have on metric space. Okay, in metric space, we define neighborhood to be something that contain an open set. Okay, but this one is exactly the open set itself, so we will call it an open neighborhood. Okay, and this is also following the convention of Richmond in the book by Richmond. Okay, so be aware when you look at neighborhood, is it open or not? Is it not open? Okay, just be aware. But we will fix this convention in our course, our lecture notes. Okay? Whenever we see open neighborhood, is an open set that containing X. All right. So last time we mentioned closed set. Okay, we define closed set using the complement of open set. Okay. So it is similar to metric space. We are going to define a limit point. Okay. So if suppose that of a topological space and there's a point in X, we say that S is a limit point. Or last time we also used cluster point. And similarly, also the accumulation point. Okay, so this is the same convention in Moncrief. Okay, how do we define this point last time? Anyone remember or not? Limit point in metric space. Yeah. I thought Jin said I want to volunteer. So how do we define limit point in the metric space last time? I can recall. Every open ball has a sorry? Yeah. Every open ball, where is the open ball? Who's open ball? Huh? center and X. What about that for contain? Can contain other element in the metric space other than itself. Right? Okay. So similarly here, there's no ball here already. So we replace the ball to be open set. Okay, we just replace the ball as the open set. So if every neighborhood, open neighborhood, okay, is every open neighborhood of X intercept A in some point other than X. Okay, remember that last time we said that a set intersect another set when the intersection is not empty. Okay, or another way to say it is S is a limit point of A if it belongs to the closure, okay, to the closure of A take away X. Okay. So if it belongs to the closure of A take away X. Okay, so last time I've shown you the picture, right? Okay, this limit point here might not be in A or might be in A. Okay, it doesn't matter. Okay, it doesn't matter. So X is in A or X is not. You might limit to something that's not in the set. This example is like a typical example is the rational number converge to irrational. Okay, you might convert to something outside the set. Okay, so maybe we do some It's a limit point. It's okay. Any question? Okay. Maybe we do some very quick example to check the concept. So for example, for this set here, what's the limit point of this set? 1 over n. So you get like 1, 1/2, 1/3, 1/4, and so on. So what's the limit point here? You need to check that every neighborhood of that point intersect this set here, right? Other than itself. Can any one of the n be limit point or not? Why? You can just build some, you can find some epsilon such that the epsilon neighborhood is excluding the neighbor points, right? So which point you cannot do that? Or which point? Or any point that can, 0, right? 0. So for any epsilon, there exists a n such that 1 over n is less than epsilon. Okay, so this is the Archimedean property. And so 0, so 0 is the only by definition. You check my definition, okay, using the Archimedean. Okay, right. Okay, so of course, you don't just check 1 over n, right? You should check all the x such that x is not 0. Okay, you need to show that they are not the limit point of b. But for all those number, you can always find a epsilon ball such that epsilon interval such that it avoids this set here. Okay. All right. So there are some theorems that we want to quickly run through, but might be skipping proving them because they are really similar to metric space. So again, let's look at a subset of a topology. So if we consider all the limit point of set A, let's call it A prime. What can we play around with this limit point in A? Okay, it's just the closure. Okay, if I take the union of A and their limit point is just the closure of A. Okay, so there is no surprise result here. Okay, there's no surprising result here. So this is really similar to what we have done in metric space. Just that we replace the definition of closure as an intersection of closed set that contains A, and we replace the definition of limit points, okay, by using open set, okay, instead of open ball. Yeah. Yes. Oh, sorry, all limit points, I skip it. Yeah. Sometimes my hand cannot work. Also cannot work with my brain. So just check with me if I make some mistake. Okay. Okay. So let's see what else. So a corollary here would be so a subset of topology is closed. Okay, if and only if it contains all limit point. Okay, topology is closed if and only if it contains all limit points. Okay, so this is really a small result from the above. Okay, remember that last time when we introduced the definition of A bar, right? So if the set A is closed, or really it's a if and only if statement that A is equals to A bar. Okay, this is what we know, we discussed when we introduced A bar. But the above says that A bar equals to A union A bar. Okay, so meaning that if a set is closed, you should contain all the limit points. But just now, we remarked that this limit point of A might be in A or might not be in A, right? So if it is closed, then it must be in A. Okay, it must be in A if it is closed. Okay. Right. So you see here we connect closeness with limit point. Okay, but when we define closeness, right, we didn't really mention about this limit stuff. We just define closeness as a complement of the open set. Okay, then we relate to this limit points here. Okay, to how to say to connect what you know about the closed interval, for example. A closed interval will contain all its limit. Okay, if you make any convergent sequence, okay, inside closed interval, it should have a limit inside the closed interval itself. Okay, so this is what trying to imitate. Okay, the real number. Any questions so far? Any questions so far? Yeah, any questions? No. Okay, so one thing I want to say is I think I'm quite direct. So if you have anything you want to point to me, right, please don't be shy or 不要不好意思, I mean, okay. Even if you are wrong, right, I won't laugh you one. Okay, so it's okay. If you are direct, you have a direct question or you have direct suggestion, you just point out. Okay, then we straight away discuss whether this is true or false. Okay, we don't want to have too many say too many unnecessary um, unnecessary um, necessary what? I don't want to have too many unnecessary useless communication. Okay. So if you have any problem, okay, you think it's a problem, okay, say it. Okay, I won't knock you on. I won't. We will just discuss whether this is right or wrong. Okay, and then the problem is I just want to make things go. Okay, I just want to make things keep going. Okay, yeah, I'm very direct. Please don't one more I don't like. Okay, okay. So next, last lecture, I put some what's that? Mm, uh, well, suddenly forgot the word. Okay, I put trailer on this Hausdorff space. Okay, Hausdorff is a mathematician. So what's a Hausdorff space about? So let's do some motivation first before we introduce again this definition of Hausdorff space. Okay, so so in the normal space that we know, right? For example, R2 or Rn. Right? So you can see that you can verify that each uh, one point set is closed or the singleton set is closed. How to verify this? How to verify this? Is what? Say again. Say again. Why are you doing that? Huh? Right. One way to do this is to show that the closure of this set is itself. Okay. So you can see from you can show that the closure of this set is itself. So how to show this? Go and find the limit point. Okay. So you can literally take any point in R and show that if it is a limit point of this set or not. Okay. But to be a limit point of this set means what? For every neighborhood of that point must intersect the set. Is it possible or not? Is it possible? If you take smaller open neighborhood, right? Or in this case, just interval, or maybe open ball, right? You can avoid this point easily. Okay, just compute the distance between the two. Okay, and then take uh, radius less than that distance. Okay, you can avoid it. Yes. Yeah. I mean, sure. I mean, there are a lot of points very really close to this point. Okay, but the point is, how do you decide whether S is a limit point of limit point of S naught? No matter how close, right? You still have a distance gap there, which is you can compute it d of x S naught. No matter how close, epsilon close, still epsilon distance. Then I use that epsilon to build a open hole. Does it make sense? And this is true for all x in the real number of R2 or Rn. Does it make sense? Yeah, no matter how close, no matter how close with you, I still have distance with you. Does it make sense? Or you cannot say I am very close to you and then I can do anything. No, we still have some distance. Yes or no? And so this is metric space. This is the space you live in. Okay. Right. So, but the set case is but this is not true for any topological space. Okay, this is not true. For example, there's one example we can see already. Last time we considered this kind of example. So a 3-point set topology. Instead, we will pick this one following the example in the book. So this one here. So let's call the 3-point A, B, and C. But this is not true for any topological space. Okay, this is not true for any topological space. In particular, this one. Okay, which 1-point set is not closed here? Which 1-point set here is not closed? To say a set is closed, you need to look at the complement. Complement of what set is not open? B. Okay, so if you take X, take away this set here, is not open. Because we didn't include this guy here. Okay, it's not closed. Okay, in general, this is not true. Okay. Another thing before we go to that definition, that example, we should talk about convergence first. So in a topological space, okay, a sequence x1, x2, of points, so a sequence of points of the space x, of x, we said that it converges. Okay, how to talk about convergence here then? Any idea? So convergent in metric space is what? Yeah, convergent metric space is what? Oh, this is a MA1 that I taught. Let's recall your MA1 knowledge. See convergence of a sequence. Convergence of sequence. What's the first thing you need to take? What's the chance for every epsilon that exists n? Where's the delta? Here there's a sequence here, right? There's an n such that for all small n greater than n, all the an behind the capital N minus the limit, and the absolute value of it is less than epsilon. Okay. So here there's no open interval here. So what we have is if every neighborhood u of x that exists similarly we have natural number, or you call it a positive integer, such that Sn is in U for all n greater or equal to n. Okay. So this neighborhood here, how to say, replace your epsilon ball. And actually, this neighborhood is better than your epsilon ball, you know. Your epsilon ball is like symmetric around that point. But this neighborhood can be just any neighborhood that surrounding your x. Okay. So my neighborhood can look like this, can look like this, can look like something else like this. But your epsilon ball should be symmetric here. So it's like epsilon minus epsilon like that. Very regular. Okay, your epsilon ball very regular. My neighborhood is just some random open set. Does it make sense? Make sense or not? Okay. Okay. So potentially this one is stronger because I include the regular open ball. All right, so this is convergent. So the next example we'll talk about is next observation we'll talk about is observation 2 is in the normal Rn case, right? Okay, a sequence cannot converge to more than one point. Sequence, okay. Sequence. Yeah, correct. Okay, cannot convert to more than one point. Okay, did you guys prove this before? Limit of a sequence is unique, where you just take suppose there are two different limits, okay, and then you can bound it by triangle inequality, right? Wait, what am I writing here? Converge to cannot or cannot. I leave out the cannot. Cannot converge to to more than one point. Okay. So yeah, so you take two limits and then show that they are within epsilon together. Okay, using triangle inequality. Okay, so this is really special about this Rn here. Okay, so for example, similarly, you can look at this previous example here. Let's look at this previous example here. So how about look at the sequence an defined to be B for n. Okay, so ask where this sequence converges. Okay, meaning what? You need to take every neighborhood of the limit point that you think is a limit point for this guy, and then show that B is always in there. Who is always with B? Huh? A or C, right? So, I mean, every neighborhood of A contains B. Every neighborhood of C also contains B. So you can potentially converge to A and converge to C. 是一脚踏两船。So you see, they live in the same open set. Okay, right. So you can do weird stuff with this topology. Okay, so far any question? So we want to avoid this. Property here. So how do you avoid this? So to avoid this, we introduce Hausdorff space. Okay, so this is the property that really characterize our normal Euclidean space. Hausdorff space. Topological space is a Hausdorff space if for every pair x1 not equal to x2, okay, in X, there exists a neighborhood, okay, there exists neighborhood U1 and U2, okay, and this neighborhood are of x1 and x2 respectively, okay, respectively, such that U1 intersect U2 is empty. Or we say that U1 and U2 are disjoint. So for what is Hausdorff space? You take any 2 points, okay? You can form an open set around it that avoid each other. Okay. Okay, yeah. So talk about more relation. So you can think about actually human relationship using this spaces. All right. So first theorem we can establish is so every finite point set, again, not just singleton, but every finite point set in Hausdorff space is closed. Okay, so this is trying to generalize the result in Rn. Okay, but to show that every finite point set is closed, really it boils down to prove that every singleton is closed. Why? Why? Why does it boil down to a singleton set is closed? Because you are just taking finitely many of them. Okay, if you take it arbitrary, then might not be. If you take infinitely, might not be. But this is just finite. Okay, so it suffices to prove that it suffices to prove that every one set of singleton set S0 is closed. Okay. So I won't proceed with the proof because it's really similar what happened in Rn. So you can try and complete it. Yeah. And then so you might ask, is it true that all topological space uh, that has finite point set is closed is Hausdorff? Okay, you might be tempted to ask this, whether the other direction is true or not. Okay, actually it's not true. Okay, so you can take an example that, for example, the real line R in the finite complement topology. So recall what is the finite complement topology. So a set is open in this topology if the complement of this topology is finite or is the whole set. So this under this topology, real line is not Hausdorff. Okay? It's not Hausdorff, but it is a space that its finite point set are closed. You try imagine on what's happening here. You try imagine what's happening here. So meaning that if you take 2 points in real line, okay, consider any open set around this 2 point here. You can't avoid intersection between the two open sets. So you need to think, wow, how big should this open set be? I really cannot avoid it. Okay, but at the same time, it is a space with finite point set are closed, meaning the complement of this set is just open. By definition, of course. Okay. So why is this true? How should you think about the open set in the finite complement topology? How should you think about it? Find a basis for finite complement topology. And so try and find the basis for TF. How does it look like? You mean open interval, close interval? Open. Like this. Like this. Is this true? Is this open in this finite topology or not? Yes or no? You just take X, take away this guy here. Is this guy finite or not finite, right? Okay. You need to include more stuff. Okay. The real line is pretty large, right? We know that it is uncountable. Okay. So if you want to be you want to be finite, you need to take away how many things? Also uncountable things. So your open set is really uncountable. What are the uncountable set here? So this is an uncountable set minus n to n, but seems like not big enough, right? Sorry, x minus negative n to n be the be the open set. Is this finite or not? X minus 100. You mean which one? Which one? X minus which one? This one? Is it? Never mind. Okay. What can we do? What else can we do? Maybe we can try some example, right? Maybe this example, finite, right? What's the thing inside here? Just n. Okay. And what else you can do here? I can really include like things like this. For example, like that. Okay. And uh, is it enough? Is this all what you can do? Is this a basis or not? I just found some open set inside here. This is a basis. Yes. Yes. Sorry. Yeah. I mean, does all the basis element looks like this kind of union of open interval? If you take intersection of these two kind of things, and you find another basis element that lie inside it. Cannot. I mean, just do some experiment. Cannot just think. You guys need to take some example, right? So, for example, let's make it smaller. Okay, let's make it smaller. Something like this first. And let's say we claim that this kind of thing form a basis, so this two kind of element should be in there. So if we intersect these two things, these two, let's say, potentially our basis element here, what do we get? We get minus infinity to 2, and then union of 2, 3, and then union of 3 to infinity. Still looks like something what we want. Right. So you can try and prove that this basis here should be built up by this kind of can I say sequence? Not sequence, but finite. Sorry. Finite union of open interval with the first one starting with negative infinity and the last one end with infinity. Does it make sense? Okay, try and show that this is a basis for it. And then in this case, after you get this, then you can try and build any open interval around two different points. And then you can see that there should have some non-trivial intersection, right? Because we are including so many numbers at the end or in the front, up to infinity and up to negative infinity. But But every finite point set are closed because you can just take the complement to be written as the union of this guy. Does it make sense? In particular, I mean, if you want to say that 2 is closed, then you just take this to cover your 2, right? But this guy here is declared to be open. Okay, and then you can have a union of them if you want to consider a field. Does it make sense? Okay, so in this case here, we will define what is called a T1 axiom. Okay, so a topological space satisfies T1 axiom if all the finite point set are. So we will call it a T1 space. Okay, if all the finite points are closed. So similarly weaker than weaker. Stronger or weaker. Okay, I think we cannot comment like that, but Hausdorff space will imply every finite point set is closed. Okay. So T1 space seems to be more general. I cannot say which one is stronger, which one is weaker, but I can say that T1 space is more general because it contains Hausdorff space. Okay, so one thing you can prove here is this T1 space is not too bad. Okay, it's not too bad. Let X be T1. It's not too bad. Okay, if we have a subset of X, then X is a limit point of A if and only if every open neighborhood of X contains infinitely many points of A. Does this remind you of the property we have in metric space? Right, remember we proved some similar argument like this when we talk about closure of a subset in the metric space. So this is true in T1 space. Okay, we also have this kind of property. And the proof is a very simple exercise. Okay, we will just keep it. But the point here is you need to try and relate back with your metric space. Okay, and to achieve this, you really need T1. Okay, you don't even need Hausdorff. And so before we finish up with this Hausdorff thingy, so of course the main result of the Hausdorff is if S is a Hausdorff space, then a sequence of points of X converges to at most one point of X. So this is really what we started with. Okay. How to do this in this case here? Okay, we don't have triangle inequality to help us now. Okay, how do we achieve this? Maybe we do the simple proof here. Let's see what's the idea involved without triangle inequality. So what do we do here? Similarly, now this is a uniqueness proof, right? So you just assume or suppose Sn converges to X and Y where X not equal. Okay. So how? So this kind of proof is really what we like a lot because you really have you don't have much much information to play with. Okay, you really need to apply everything you have here. So since Sn converge to X, right? Means what? Every neighborhood of X must contain X and some point of Xn. Okay. For every. Right. So which open set are we interested in here? Which open set we are interested in here? There's the open set that the question throw to you. X is X not equal to Y. So meaning what? Meaning what? Now yet, you need to exist first. Exist what? There's this neighborhood of X and Y, which are disjoint. Okay? So since X and X not equal to Y, okay, maybe we throw this to the back first. So since this is true, there's this U1, U2. So okay, let's do this. So U1 containing X and U2 containing Y, such that U1 intercept U2 is empty. Okay, but since Sn converge to X, that means what? That means what? That means U1. So by the theorem just now, so U1 contains infinitely many points of Sn. Infinitely many points of Sn. So in the textbook, right, you will see that it saying that for all but finitely many value of S, and meaning it might avoid some finitely many term in the sequence, but in the end, you still contain most of it. Okay, in the end, you still contain most of it. So if you want contain infinitely many points of Sn, right, can U2 do the same or not? Cannot. Why? Because there's no intersection between U1 and U2. So you found an open neighborhood around Y that doesn't do the limit stuff. So it cannot converge to Y. Right? Yes.
Is if we let x x1, x2, x3, x5 be u1, x2, 4, 6 to be u2. Are infinitely many points in u1, u2, right?
What do you mean? What do you mean? Do you want to construct an example now? Do you want to construct an example? So U1, U2. Yeah. So you want X1 lie here, X2 lie here, is it? And then what else you want to do? X3, X4, X1.
Converges to x, x even. I mean, not converges, but these are infinitely many points in u1, u2.
Sure.
Yeah.
And then I mean, does this sequence converge or not? If you do this, does this sequence converge or not? If it doesn't converge, then how do you talk about it, whether it converges to one limit or not? Does this converge or not if you do this? You are somehow like doing this, right? Minus 1, 1, minus 1, 1, 1, minus 1. Converge or not? Yeah.
Yeah.
Yeah, so I suppose it converges. I converge to two things. Converge and then converge to. Yeah. They have to converge first. It doesn't converge, then of course. Yeah. That's the point of non-convergence. Yeah. Okay. Now. So if U1 contains infinitely point of Xn and U1 intersect U2 is empty, meaning what? U2 cannot internally and in terms of yeah. Yeah, that's why I mean if you can do that, then you can produce a contradiction that this sequence is not converging. If can, then you can produce the contradiction that Sn is not converging. I mean, a bit crazy. So, I mean, I mean, yeah. I mean, okay, tell me what you want to do. Okay, tell me first what you want to do. I think you guys are confused what we are trying to do. You guys are locked inside the working, but you don't know what you want to do. Okay, so tell me what you want to do. Tell me step by step. What? Cannot tell. You need to say a plan, right? And then we execute the plan. You cannot just say, "Oh, I tell you this, do this, cannot do this, cannot do," and then you don't know what you want to do. Then how to discuss, you know? So the problem is you need to understand this. Yeah. If S is top dots, then a sequence of points of X converges to at most one point. What does this mean? Tell me. Do we start with convergence sequence or not? Tell me. Don't know. We start with convergence sequence. This is what it says. It converges. Okay. What we want to prove is it converges to at most one. I'm not trying to prove whether this sequence converges or not, because I can come up with a non-convergent sequence. What for I want to discuss that? I want to discuss only the convergence sequence. And then this convergence sequence converges to only one limit. This is what I want to do. I'm not discuss, you give me a sequence whether I know this is convergent or not. No, I start with a convergent sequence. You get what I mean? So, so if you try to say what you want to do, let's say it's also content, then there's a contradiction. So meaning, yeah, so there's a contradiction. So still there's only at most one, right? Because you have a contradiction. It's a contradiction proof. Yeah. You get what I said? You get what I said? Okay, so yeah, you need to understand statement first. So normally, if you like your head is very heavy, right? Like when you listen to what I say, right? It's because you haven't know what I'm trying to do. Okay, to make sure what I'm trying to do, you need to get the first statement right first. So always, when I write down the definition, right, or write down a theorem, I'll ask you, you understand this theorem or not? You understand the definition or not? Okay, I not simply ask for fun, because I want to make sure you can follow what's going to come. Okay, does it make sense? Okay. So if you have wrong idea about this definition or wrong idea of the theorems, right, you have to quickly raise it up so that we can avoid some unnecessary discussion. Yeah.
Professor, is theorem not mean if to no point of F, then between is diverge?
We are debating. So if you say it diverges, so diverges could be, I mean,
because atmosphere can be no point.
Here could be made most 1.4. Yeah. So atmosphere could be no point. No points mean what? It converts to somewhere not in X. It's like rational numbers. So yeah. So if you like, maybe this is what it means. It could converge to something outside the set. It's like rational number. You converge, but you converge to irrational. It could converge, okay? Because if you take constant sequence of rational number, then it's boring. Just converge to the itself. Okay. By the way, don't take it don't take it personal. I'm not scoring you. By the way, I'm just trying to reasoning. Maybe if I hurt you, but sorry. Yeah. Yeah, it's okay. Just Just now we are not how to say, I'm not scoring you, we're just arguing. Okay. Yeah, so please don't make it personal. Okay, I don't like that. You can also score me one if I'm wrong. And I won't like, wow, 我恨你一辈子. Not like that. It's not like that one. If you do like this, cannot improve already. People say you a bit, then you 生气 like that. For what? If you're wrong, then you change lah. Correct or not? If you're not wrong, then do yourself wrong. Why want to 生气 like that each other? Why like that? Personal, right? But I know this is personal. This is personal. But this, I think this is the right community that we should do. Yeah. So don't try to be too ego. Take away your ego-ness. You can choose to keep it. Like Jin Xian said, if it is personal, you want to keep up. I can telling you, you will be destroying self-destroyer if you try to keep ego-ness forever. Let me tell you this. Let me make it very clear. You can try and keep it, but this is a self-destroyer. Okay? If you don't believe me, go and try it. I'm a mathematician. You prove to me. I prove to you now. If you don't believe me, you go and try it. See if you got contradiction or not. If you don't got contradiction, come back and tell me again. Yeah. Seriously. Yeah. So I mean, yeah. So if there's mistake, we just discuss. We just discuss based on facts. Okay. If I'm wrong, then I will admit I'm wrong one. I won't just push you, force you. What? No. But this is true discussion. This is true discussion. We need to keep constant communication. Okay. Yeah. Maybe sometimes I'm I'm very stubborn. But I'm trying to like accept if you have a point there. Okay, so you need to take point. You need to hit me with point. You cannot, just randomly say. And I also have to hit you with point. Then you will accept it, right? Yeah. So this is logic. That's why we establish logic, reasoning. Okay, why this is true, why that is true. Okay, this is the key. Okay, it's not just some random abstract. All right. Yeah. So let's take a break. Let's take a break for 10 minutes, and then we will come back for continuity. How we can income for
I had some problem moving the
comparable
metric.
Some more times.
I have already done the assignment, but I figure out I have to submit it at once, so you don't need to find all my workings separately.
Oh no! You submit 1 to 1, 2 to 2, 3 to 3.
Oh yeah.
Yeah. Don't put any together.
No, I should send.
No. You just submit 1 and 2 first if you are ready. So 3.
Only 1 hour that.
Okay, sure. So how much more time? Because I want to
I
close
can
it
do it today.
today.
Yeah.
Okay, because I want to close it by this Friday. I don't want to drag too many because also no problem. How about you? 三没有，可以先交嘛？3呢？你需要多点时间吗？明天哦，可以，OK，没问题。可是把
这1、2先交
1、2先交。But 我有发一个邮件给你们 ，email 没有注意到？check 一下，一定要check邮件，不然的话我没有方法联络你们哦。对，所以你们一定要check邮件跟 Teams。OK 吗？能交不能交你都要回一个，不然的话我会觉得你是中的，所以你不知道怎么办。
叫什么？上个礼拜是
第二时间，
我一直以为4点半
对，OK，可以，没有问题。
Okay. So about proving of the comparable matrix equivalent file, could you give me some instructions about?
Can.
Wait, which should I prove it?
I forgot the question.
Set is within each other.
Oh, yeah. Okay. You just need to show inequality.
About.
Okay, inequality. Yeah, which inequality? Maybe I just show you what's the inequality is. Wait, you need to show some inequality. Okay, let me open the question first.
Someone change question 2. This is something again.
Summon 3.
Sponsor.
Oh, this one, huh?
Yeah.
Oh, okay. This one, yeah. This one is just you assume this, okay. So to show that one thing is open than the other, right?
Yeah.
You take an open ball in XD1. Okay, you want to show that it is open here. So what does it mean by? What do you mean by an open set in D1 is open in D2 here? So you need to find for every point in this open set, you can find an open set in XD2 that contain in
So it's like you repeat the same, right?
yeah. So okay, the full question, just for definition. U is open in D1, XD1. If for every X in U, there exists a ball of D1, let's say R1, okay, this is in D1, X such that this thing is in
This is within you. So
conversely,
the D2
for D2 is also the same.
Okay.
So now the problem is if you want to take this open set in this symmetric space here, how do you show that? How do you show that there exists a BR2 at D2 that's contained in X? Contain U. So what can you do? You know that this guy is in U. So you need to choose R2 such that this ball here is in BR1 D1X.
And BR1 is containing B2 set. So
And then the other way. This is one direction. So how? I mean, you can try this. I forgot which direction. Okay, should be R1 over A. And then you can make sure that all these points here is within around.
or define R2 as equals.
Yes, because you need to know that these two distance is related by Tx dy(x1) less than equals to A d2x1. And then you put this in here. So meaning that all these point here is within.
So that's what the statement was.
Yeah.
I just confused why.
Yeah.
The statement will
Definition. So you need to one first is comparable definition. Second is this definition. Yeah.
Can I snap photo?
Yes, there's a. I just send you.
You can directly send you.
Yeah, I sent to your. I got your.
Do you need
Things right.
Yeah, still hang on. You don't need my still idea.
I don't think so. I can search by your
CHAG. HAO.
Are you a Malaysian?
Yeah.
Oh, you're Malaysian. Oh, no.
Even Johor.
Oh, Johor Bahru. Quite a lot of Johor people in this class. I mean. Why I can't send you? Sometimes these apps got problem. Okay. Which year are you in?
The last year.
Oh, last year.
Actually, a development semester because my FYP had got some problems.
Okay. I sent you.
Okay. Thank you, sir.
Yeah. Thank you. Yeah.
这个最后一题
也是
，dual proof 的 dual lemma 是 proof 这个吗？
是不是这个
还要做这个？
没有，就是 prove 这个 prove 这个，都懂，就是它。对，就是你要说的每一个 open set 是个 union 哦 ，fundamentally many closed set。要不是 C 的 complement
不要死。
想一下，this shows that every closed set in a metric space, every closed set is an intersection 的一个，所以我拿它的 complement 是一个 open set。And then complement of intersection 是这样是好像是是一直 complement OK，好，那下面3看，看没有？这是个
24
哦，OK，
对吧
？Yeah，2分钟，还有
就这个 S 的题是所长是这题是 topology
T 是 topology，X 是 space，所以 topology 的 space。topology 合起来还是一个 topology space。对啊 ，topology 是告诉你里面哪个 subset 是 open。
所以 X open。
X 应该要 open，因为每一个 topology 它都要 open。对，每个 topology 都要有 X。然后
像这个举这个例子，
所以我就不懂，这么为什么这个 topology，因为
我 define 的，你不知道就是要 prove， 你要 prove that 它是一个 topology。为什么我这样子做它还是个 topology？ 你要 prove， 就是要 prove 的。
没有，I mean 我讲这个例子嘛，然后这个东西它引我找不到，我就找不到它引这个。
哦，这样你要了解这个 R 上面 topology 是什么事，你才知道 R 上面的 open set 是什么。你要知道为什么我只写 R。很多个 topology 我可以放在 real line 啊，这么我先写 R standard topology 咯，这个 R 就是普通的咯。然后我们可以形容这个 standard topology 用 open interval 罢了，所以每一个 open interval 都是 open， 这样子哦。OK，再说一下。So we will talk about continuity now. Okay, continuity of functions. Okay, do you see continuous function? So did you see open interval in the definition of epsilon delta continuity? Did you see actually? Or maybe someone can tell me what is f from R to R to be continuous using epsilon delta? You know, recall? Okay, so let's say this is continuous at where? At a point x. At a point x. At x. So for every epsilon greater than 0, there exists a delta greater than 0, such that what? Purposely, so we need to find. So one other thing you guys need to learn, right, is to think idea instead of see a real stuff. You get what I mean? You cannot just remember word by word, symbol by symbol. You need to be able to pull yourself outside from this symbol stuff and then try to think about what's S not representing. Okay, so this will differentiate you between, like what I said, maybe most of the applied maths. I don't want to say all of them. Most of the applied maths and pure maths, because
you will be focusing on the abstract stuff behind the symbol. Okay. So let's say I pick x is the fixed point already. I fix x. So I need another point. What do? I just pick another symbol. So let's say I say for every y in R such that absolute value of y minus x less than delta implies fy minus fx less than absolute. Okay. Did you see some open interval here? You see or not? You see any open interval here? Fx is some fixed point. Right? So what is fy minus fx less than epsilon? This is a epsilon ball around fx. So here is fx plus epsilon, here is fx minus epsilon. Okay, so you see we put strictly less than, strictly. So there's an openness here. Strictly. If I put less than equal, then it might be close. Okay, how about the other side? The other side we also have this open thingy, right? So this is open around x. So all the y that live around this open. Okay, so all the y should be live around this open interval here, and then fy should be live around. Does that make sense? Okay, so you see, you want to make sure there's an open set in the codomain. You rely on some open set in the domain. Okay, so in other words, we will make this abstract. So let's define a function. Okay, so I mean, let's start with two topological space. Okay, by the way, if everyone still don't understand this notation here, need to be a bit careful because I keep using this notation. If you don't understand, meaning you don't understand most of the statement I've said. So if I put S tau means what? S is a set, is a space, and then tau tells you which subset is open, which means this is a topology, okay, on X, right? Okay, so let's say we have these two topological space, a function. So this function is defined on set only, you see, X to Y. Okay, we didn't talk about openness. Later we will mention how this function relates open set. So this function is continuous. For every open set in Y, let's say V Y, the inverse image of V is also open in X. Okay, so you see there are two openness involved here. It's different. One is open in Y, one is open in X. Potentially X and Y could have different topology. Okay, so you just require that every open set in Y, the inverse image of V is in X. Okay, so this really generalizes the epsilon delta definition. Yeah. Okay. All right, so some remark here is so this function here, so continuity of f might depend on the topologies. Just put one topology of x and y and the definition of it. Okay. Later we'll see example. If we swap topology, if we keep the same function but we swap topology in the domain or codomain, we might get the function not continuous. Okay, in this sense. So sometimes we will say that f is continuous relative to the topology we have on X and Y. Okay, not just, it's not enough to just specify what is the domain, codomain. You need to know how the subset are open there, because you need to check for every open set, okay, in one, such that inverse image is open as well. Okay. All right, so maybe let's jump to some, yes. Hey, so I forgot again. My then also haven't finished. Then this thing is then sky is open. I try to put some short form here, but too short. Okay, I try to put some short form, but too short. Okay. Yeah. So for every open step in your codomain, the inverse image is open. Okay. Every PY is open. Open in the topology. So what do I mean by open in the topology? So there are few ways, right? Few ways to look at this openness. One way is I tell topology, immediately I will tell you what things are open. So this is defined by the topology. Topology say what's are open, everything clear. Okay, but sometimes to check things is a bit how to say a bit troublesome, because you want to check all the open set. If you all the open set is infinite, how to check? Okay, so sometimes if we know the topology is generated by basis, then we can reduce checking all open set to checking just the basis element, because we show that if a topology is generated by a basis, it means that all the open set is just union of basis element. So you just check on basis element. Okay, then in that case you will say how the topology is open in terms of this basis element. Then we go back to the start of the definition of a basis of topology. So how we define a topology that's generated by basis? How do we call open set then? It is open, a set is open if every point inside the set, then you can find a basis element that contain the X, and then that basis element contained in your U, the open set that you want to think of. Open. Remember? Okay. Yeah, so there's something really going on here. Yeah. Okay. So what example we should take? So just now we already do examples, right? So examples in continuous function in one-dimensional, continuous function in one-dimensional. So you can try and show that this openness continuity. So let me bracket here. So using the openness continuity, this is equivalent definition with the epsilon delta continuity. Yeah. So if it continuous in the open sense, then it also continuous in the epsilon delta sense. If it continuous in the epsilon delta sense, it's continuous in the sense of open set. Okay. So I'll try and show this. Actually, if you have gone through calculus 2, right, there are more continuous function you see, not just between R and R, right? Between, for example, so let's say I put here continuous function from R to R2. So you swap between two topological space here. Although their topology is similar using standard one. So what kind of function you get here? This function here. The thing you see in the calculus 2. R to R2. What is it? You're putting real line into R2. Oh, no, yeah, too far. Oh, okay, it's a vector value function, but we can describe it simpler a bit. It's a vector value function, yeah, correct, okay. But what is this? What is the object we're looking at here? If it is continuous. How to think of this? So really, you just try to take real line put into R2. So these are just curves, okay, curves in the plane. Not that this one is continuous, so this is curve. Maybe you can get something weird if you don't consider continuity here. R to R3 then, also curves, okay, so you can think of like the particle run around the space, right? So if it's larger, then we call it a space. And what else? We can consider R2 to R also, right? This is what we learn, multiple integral, okay? If it's continuous, only it is integrable, okay? So you need to start with continuity. And also R3 to R, really what are all these calculus 2 is doing? And more generally, you look at the vector field. So these are all continuous functions between topological space. Okay, now you think of it as a topological space. Okay, what set are open? Open in the sense of Euclidean, or sometimes called the standard topology. Okay, or not? So now I give you another example here. The identity function might not be always continuous, right? So, for example, here. So if we regard the normal one, R to R, okay, we will prove that X is continuous. This identity function is continuous. And then you prove that the power of it is continuous, right? And then so on. Then you establish that the polynomial functions are continuous. Okay, but there's some, if you change the codomain, right? If you change the topology of the codomain, then this function might not be continuous anymore. Okay, how can we do that? How can we do that? Can we change this topology a bit? Okay, let's change it to let's change our codomain to a lower limit topology. What's the basis? Last time we discussed about this lower limit. Lower limit means what? I want to take the lower number, left endpoint of my open interval, right? So this one is generated by. Okay, so maybe I do like this. Something in here is like this. So it's a half open interval. Okay, so this guy is declared open in RL. What's the pre-image under this identity map? Let's say, for example, we take this guy here. What's the pre-image of? It's the same, right? But this is not closed and not open in the standard topology. Okay, so identity function is not continuous. Okay, with respect to this two topology. Okay, so weird thing might happen. However, if you change the topology in the domain of codomain. Okay, but if you do the other way around, it's fine. Right? Is it fine? It should be fine. Okay, if you change the other way around, it's fine. Meaning you look at RL to R. Okay, show that it is a continuous if you consider identity function. Okay. All right. Next, what time is it? Okay, so we can look at a few theorem. Few properties of f being continuous. So let f be a map from st to y t. Okay, ty maybe and tx. 1. So 1 here. F is continuous. Okay, so what am I trying to do is I want to introduce a TFAE statement here. So these are equivalent. So these statements are equivalent. So 1, F is continuous. 2, for every subset A of X, again, one has f of the closure of A living inside the closure of FA. Okay. 3, for every closed set B of Y, then the inverse image of B is also closed. This really, how to say, resemble what open set does, right? By definition of continuity on open set as well. Every open set in the codomain, the inverse image is also open. So this is really resembling what the openness does. The fourth one will be for each x in X and each neighborhood. Okay, each neighborhood. So neighborhood here, if I forgot, please remember this is open neighborhood that we define. V of fx such that there exists an open neighborhood. Open neighborhood U of x. U of x such that fu is in V. Okay. The fourth one is kind of resemble what we have for epsilon delta, right? If you start with a neighborhood of fx, okay, and then there's a neighborhood u of x such that when you map across, it lies inside the V neighborhood. Okay, this is really resemble what we have epsilon delta, but more flexibility here. And maybe one non-obvious here is 2, maybe not obvious to me. You're trying to think about this one here. For every subset A of X, okay, if you consider A bar, meaning what? You consider A with its limit point, okay, and then you map it across. You map it across. And then these points should be either a point of FA or limit point of FA. But you might not achieve all of them. You haven't achieved all of the limit point of FA. It's not as complete. So if you want to consider FA bar, maybe you need to do more work to complete it. Complete in the sense that you put in limit points. Does it make sense? Okay or not? You know how to think about this statement here? So you should start from the end. So maths have this weird thing. So although we write in this sequence here, right? But really what we are interested is the thing at the most behind. Okay. Like the MA1 student asked me, hey, sir, why I put n first after and before epsilon? Right. So every time when we do the work, right, we start with calculating the inequality. We want to make sure the inequality works first, and then we know what n we're going to put. But when we present to people, we tell people that, hey, we choose n first. Only then what things I would. Only then the inequality will work. But when we really go to make our hand dirty, want to show it, we need to really get the goal to work first. Okay, in this working here, only then we can determine what n we want to use. And then we tell people, okay, this is the n we want. Okay, but yeah, but a lot of people maybe take it for granted. They will ask, including me, when I first learned the maths, they say, huh? How you get this n? Follow first, choose this n, okay, then I will use this later. Okay, so this is the flaw of mathematical writing. Okay, so in this case here, what's the most important thing we care here? What's the most important thing we care here? Actually, we care about FA bar. The last thing. What is FA bar? I tell you what is A already, right? So FA is determined. I just simply apply F to A. FA by, I also taught you, right? Closure of a set, meaning what? We prove quite a lot of property of closure of a set. You can learn it from definition, or you can use a easier description. FA bar is just FA union limit point of FA. Okay, so here it's telling you what? How to find FA and FA, limit point of FA. Of course, you can immediately apply FA, right? But here it says that F of A bar is still a point in FA bar. So meaning either it is FA or it is a limit point of FA. But there's no equal signs here. No equal sign. Meaning what? It's not enough to build the whole closure of FA using FA. So the limit point of FA might not be the image of F. Alright, so this is what you need to show. But proof is quite straightforward. But you see, this statement here is really alive. You need to make it alive. Mathematics is like this one. You see a lot of word, a lot of definition, a lot of symbol. It's very boring. You need to make it alive. Then this segment will make sense to you. Okay. So this is the thing you need to develop. This is the skill you need to develop. Okay, when people tell you a statement, you need to start and think what is going on here. Okay, what I want, what is interesting, what is interested by them. Okay. Does it make sense? Okay. Okay. So we will left the proof as exercise. Very short proof only. If you go through the book exercise, yeah, just apply definition. Okay. Okay. What time is it? 12:41. Okay, we still can go a little bit further. So let's go further. So this proof left as exercise. By the way, even though I say left an exercise, if you don't understand, you still can raise it up next time. Okay, just that I want you to try it, and I don't want to spend time talking about it. Definition. So finally, we got to this homeomorphism now. Okay, so remember, I'm like sometimes I'll use this in class before. So what is a homeomorphism here? So similarly, we have two topological space. Okay, and then we start with bijection. F, going from X to Y. Okay, so we will say that then F is a homeomorphism if both F and F inverse. Okay. It is a bijective continuous function, but bijective continuous function is not enough. Or maybe you just say that it is a continuous function that is bijective. But in this case here, we require the inverse image to be continuous as well. Okay, only then this is a homeomorphism. You know what is homeomorphism? What is homeo? You want to know? I go back to find what's the Latin word about this homeo. What is homeomorphism? Morphism is what? Morphism is morph, form. Okay, morph, you know morph? Morph is a form, but there's nothing called morph, right? Butterfly. The younger form of butterfly is also morph, right? Is it? I don't know. Okay, go ahead and buy. Yeah. Fei Oh, it's spider. Okay, yeah. It's another butterfly, right? Okay. Family of butterfly. Family of butterfly. Okay, morph is a family of butterfly. So, yeah. Right. Okay. So homeo is what? Go back and find what is homeo means. Okay. Homomorphism same meaning same form, right? So what is homeo? It's the same one. Yeah, go back and find what is the Latin word of homeo means. Okay, so in this case here, what it says? What it says, in this case here. So in this case here, we will say that F is a bijective correspondent such that Fu is open if and only if U is open. So you send open set to open set. Just now we just say that the pre-image of open set is open, right? But now you are sending open set to open set. Because inverse image is also open. I mean, sorry, I shouldn't say that. So because the inverse function is also continuous. Yeah. Let me see, should we go a bit further? So maybe let's see some example of homeomorphism and then we discuss a little bit about this homeomorphism thing. So what kind of homeomorphism you have met? I mean, obviously, identity function is one of them. I mean, identity between the standard topology. The inverse function of the identity function is just identity. Elsa, anything you can think about homeomorphism? Sorry, translation. I think quite good translation. Translation, for example, it's key, right? For some, so I need to fix the t first. So let's fix it. That t. And the inverse is just x minus t. Yeah, so this is like an example from linear algebra. When we talk about translation, mostly will involve linear algebra because you can translate even in a higher dimension. Rn, you can translate in particular. Yeah, so right, so we have 3 minutes. So I mean we can, so let me put a non-example here. So you can come up with a lot of examples that you have seen before, but we can really have a bijective function. A bijective function which is continuous, okay, which is continuous without being a homeomorphism. Okay. How could it be? How could it be? Meaning what kind of function you are looking for? You're looking for what kind of function first before constructing. What kind of function? Adjective, continuous, but not a homeomorphism, meaning you're looking for a inverse function which is not continuous. So can you construct one function like that? Is bijective, okay, but the inverse function is not continuous. Okay, so one very nice and classic example is here. So I can define an f from the open close interval, close half open interval to x1. So what is x1 here? X1 here is just a unit circle. Circle in R2. You know unit circle, right? The distance is within 1. Okay, so I should say that this unit circle centered at where? Centered at origin. refresh this one. So unit circle. Make this map here. Okay, so this is simply the map sending t to cos 2 pi t and sine 2 pi t. Okay, is it bijective or not? Can I reach every point in x1? Why? So you go from 0 all the way up to somewhere very close at 0, but you already achieved, sorry, I shouldn't say that point 0. This point is what actually? Where the point of 0 goes to. This point is 1, 0. Okay. Okay, so what are you doing here? So you take a line, real line, with this closed open interval from 0 to 1, and then you loop it. Okay, you loop it. Okay. And somehow they connect there. Okay. So how to see that the inverse of this function is not continuous? So just now we say that if you are homeomorphism, you can prove that actually FU is open if and only if U is open. Okay. So you can really take an open set here. Okay. So the example they choose is like 1/4 here. And then you can see where this line get matched. Okay. So maybe get matched to somewhere here. F of 0, 1. Okay. But is it open or not? Or I mean, is it open in the codomain or not? So to open in this codomain, what do you need to show? This is a subspace of R2. So you need to consider the subspace topology of R. Okay, so you need to ask yourself whether this image here is it an intersection of S1 with some open set in S2? S1, sorry. Yeah. Oh, sorry, R2. Yeah. Is it an intersection of an open set of R2 with S1? Okay. But where's the open set in R2? How does it look like? Yeah, open circle or open rectangle. Yeah. So you cannot find one this how to say this thing. This is like a curve half open interval here. I mean, how to say this, right? I mean, yeah, I mean, I want to say that this thing here is not open. Otherwise, you can try and write down one open set. Try and intersect with your S1. Do you get this set or not? You can't. You can't. Because of, I would say, because of this point here. The 1, 0 point in this image. Okay, so it's not open. It's not open there. Okay, so you cannot do that. So I mean, yeah. So why we have this? Can you think of why we have this kind of maybe peculiar example here? Because 0 and 1 should really map to the same point. If we include 1 into our domain here, 0 and 1 should be mapped into the same point. But we just choose one of them. So it's enough to build the unit circle, but it's not quite a homeomorphism. So I mean, building this, right? Building this kind of stuff, you will learn in algebraic topology. Okay, doing this kind of stuff is in algebraic topology class. For here, we just learn about open set stuff, okay. And then how to glue, how to make spaces. This is in algebraic topology. Okay, for a moment, we just focus on learning the open set, closed set, limit point, and so on this space, okay, which we call the topological space. But how to build actual space is what we do in algebraic topology. We use function, Okay, gluing function. And this is kind of a gluing function. Okay, we try to glue the interval together. And one last thing before we left. So just now I make a remark here, right? FU is open if only if U is open. So this is really reminiscing when you do like abstract algebra. When you send normal subgroup to normal subgroup, when do you send ideals to ideals? Okay, this is because in there you consider ring homomorphism, right? And then group homomorphism, right? But here we consider homeomorphism between topological space. So they are correspondent between open set in the domain, open set in the whole domain. Okay. So that's why these maps are related. If your group is a topological space, then there's some homeomorphic story going on there. But if your group homomorphism is a continuous function, then you can rephrase. Okay, is your normal group an open set or not? Or is your open set is a normal group or not? If your set, because just here is set, right? Group is what? Just a set with extra property. Right? So really this thing can Malay will say campur, mix together. Once your set have more structure, you know what is open, and then set within itself, you know how to compose. Then we can mix all these property together. This is how the field connects to each other. Does it make sense? Yeah.
We take from a group to if both the group and MS is topological,
Yeah.
then is
You need to check out whether it's continuous or not. Yeah, you can check. You can check in the open sense. So you need to put topology on permax, or you need to put topology on your group before talking about continuity. So that's why every time you see this when we say this let very important, you know. This kind of let is very important because you need to start with this assumption or property first. Only you can discuss about homeomorphism. You cannot just discuss homeomorphism with random set. Okay, you need to discuss set with topology. Okay, so this let is very important. I cannot throw away this and then write to you this. And then because you will ask me, how I determine something is open? So I need to fix who is open first. Okay, then we can discuss. Okay. Makes sense? So this let thing is very important. Most important thing, I'll say. If I change the criteria, then the result will change. Make sense? Okay. So there's a lot of things I left for exercise. Please do, otherwise you will get lost. For sure. Okay, please do. Okay, I will put it in my lecture notes as well. Okay. Yeah. All right, so see you next Monday. Got replacement class. Yes. Okay, next Monday.